Yes. Sir, shall we start, sir?
Yes, sir, we can start it.
Yes, sir. There is one option will be there for a share here. Then using that tab, the share, you can share your screen, sir. While you are sharing the screen, you can use the entire screen mode.
Okay, sir.
So, good noon to one and all in this link. Uh, Today's we have the special speaker, Dr. Vivekananthan. Dr. Vivekananthan currently working as associate professor in Center for Flexible Electronics, Yale University, Andhra Pradesh. He has obtained his PhD from yes, Jeju National University. It is one of the island of Korea. He has received a grant of 45,000 USD as a PA for the research grant from Electronic in. He also worked as a research associate in University of Surrey in UK. Currently, he is the project coordinator of DST PERS program. He has received the 7 crore from the government of India. He has published many high quality papers like Advanced Energy Material, Nano Energy, small journal like many journals with the H index of 29 and I10 is 40. Sir, we are very honored to hear your talk, sir. Please, sir.
Thanks for the introduction, Dr. Shakti. And also, I thank you very much for inviting me as a resource person for the FPP that you are organizing. So I'm very privileged to provide my research talk on this FDP with my research title entitled Materials for Energy Harvesting and its Application in Self-Powered Sensing. So I'm Dr. Vivekananthan Venkateswaran, and I'm presently the Associate Professor in the Center for Flexible Electronics and the Electronics and Communication Engineering Department at Yale University, Andhra Pradesh. So first of all, I would like to introduce our research center, which is the Center for Flexible Electronics. So where we are working on the development of nanostructured materials, then flexible batteries and flexible self-powered sensors. And also we are working on the photocatalytic hydrogen evolution. Um, and we have several recent publications ranging from advanced energy materials, nano energy, small journal of power sources, international journal of hydrogen energy, JMCB so far. And these are the key research peoples that we have in our center. And Dr. Srinivas. So here, if you see that Dr. Srinivas Babu, who is the coordinator of our research center, and we have Dr. Arun Mehta and Dr. Sridhar, who are the other researchers working on our Center for Flexible Electronics on the above mentioned research areas. And in addition to that, we have around 8 research scholars who are working in our laboratory on the mentioned topic of flexible electronics and the other allied research areas. So recently we have gone to the DST PERS project, so which is the flagship project from the DST, which is about the promotion of university research and scientific excellence. So where we have received a project which entitled Novel Low Dimensional Material and Flexible Dielectrics for Optoelectronic and Microwave Devices. And so we have a big implementation group of 6 members having expertise on different themes. So this project we have subdivided into 3 themes. Like the first theme with the group of members, they would be focusing to work on material preparation, such as preparing low dimensional material, having the properties of dielectric and ferroelectric properties, then conducting polymers and ceramics, so which we would be using it for the theme 2 and the theme 3. So where they are going to design the antenna and microwave devices, liquid crystal and RF devices, and the final theme which the team is going to work on the flexible and printed electronic devices, wearable energy harvesters, and self-powered sensors. So I would be working on the theme 3 exclusively, and I have expertise in nanomaterial synthesis, where I would be focusing towards theme 1 and theme 3. And the final aim of our project is to bring a product which is of TRL level 5 or 6. And we also have plans to establish a center for excellence in this field. So through this presentation, so we are going to cover these contents like introduction to wearable electronics, autonomous electronic skin-based energy harvesters and sensors, and then we are going to see what is the need of a self-powered system in wearable electronics, and then the piezoelectric and triboelectric effects which we are incorporating in the wearable electronics, so that they could be the promising power sources for powering these wearables. And a few of the real-time applications which we have done from our laboratory would also be covered and discussed through this talk, which is to be muscular monitoring system, impact sensors, and other type of devices. So let's see the autonomous electronic skins like energy harvester and sensor. That you know that when we talk about like skin, so skin is like one of the uh, primary protecting organ of our human body. So where they can able to analyze whatever mechanical force that our body is exhibiting. Even if we get a fever or cold, like we would be the first thing is like we would be touching our skin to check whether our temperature is high or not, and the in-room humidity. All these could be balanced through our skin only. So mimicking that one, so we are going for the electronic skin. So mimicking in the sense, mimicking the physical property as well as the functionality of the skin, such as the pressure that it's going to be, the temperature, and all these could be mimicked. So it has potential application in various fields, like as I say that precision sensor kind of the sensor, and then prosthetics is nothing but the artificial limbs and hands kind of thing, and then human machine interaction, where this kind of skins can be very well used in the field of robotics. So where we can able to go for the robot can feel the sense of touch using this kind of the electronic skin based systems. And then health monitoring devices, like even you can see that these days we could have gone for the ECG or any kind of measurement. So where we could be seeing that they would be attaching a patchable electrode to our skin. So we are seeing that the electronics is now coming close to the skin, right? So this can be having a high use in the in the healthcare sectors especially. So the present day wearables, you are seeing the first generation devices here, where we are seeing the wearables are bulky, and um, it is like overweight, relies on battery and all. So in the future generation, you would be seeing that either it's going to come fabric, or it's going to be on to be attached on our human skin, or it's going to be like you can be worn these kind of wearables like a lens over your skin, over your eyes kind of thing. So we see that the requirement of power in these kind of low power electronics, like the portable electronic devices. So now you see that these kind of electronics are rapidly increasing, and we are seeing the small electronic components, sensors, all in our day-to-day life. See example in the transportation. So where we will be having our car, where we have several sensors mounted on the sensor, that hill hold assist, parking, all these are sensors. Where if you're not wearing the seat belt, the sensor is going to analyze it to give a beep over it. If you have not released the handbrake, again it's a sensor. The airbags, when it got a hit, it's going to be sensor. So all these are small and low power sensor. And when you see the portable electronics, so our gadgets are shrinking day by day, and you are holding even a computer at your palm, that kind of the shrinkable. And even our commercial home appliances also these days are becoming smart because of the electronic components which they are incorporating in it. So what is the thing which is powering mostly is battery, these portable devices, but they have several potential drawbacks in terms of using it for wearable applications. Although we are not facing it regularly, but still there are potential hazard, where the materials are corrosive and they are limited lifetime. So once you are using it for a longer period of time, so they get heated, overuse. So you need frequent recharge or replacement of battery. And we know very well that in our home, even if you are replacing the battery in your wall clock, you are not disposing it as a e-waste. We are throwing it in the general waste. Again, it's going to be dumped generally. So it's again have a potential corrosion or a kind of bursting can also be happen. So it's complicated, like recycling it and reusing it and all, or started slightly, but so far we were discarded as like us and polluted how much ever we want. So the only promising solution is development of low power energy harvesters, where we see the first one comes as the flexible solar cell, where they are very simple to develop and extremely lightweight, low manufacturing cost and all. But since you put it for wearables, when you are doing it in the indoor environment, again it has a drawback of not generating the sufficient power what we have required. And then the next one is the triboelectric nanogenerator based wearable. Of course, they are one of the potential candidate where they can able to scavenge the energy from our human body movement itself, and can be again be used directly, or you can go for a very thin kind of eco-friendly batteries which can be recharged quickly, recharge and discharge kind of thing. And then electronic skin based IoT systems are again having more potential applications, but they are going to use the effect of triboelectric and piezoelectric in generating the electrical response. So as per the law of energy conversion and utilization, so we can know that the energy can neither be created nor be destroyed, but can be converted from one part of to other. So as a result, you see this mechanical energy, which is one of the most abundant energy. Here we are talking about the biomechanical energy. So where we see that even our human body movement, even the breath, and even our heartbeat or pulse rate is also a kind of a mechanical energy for the wearable devices. So one such example that I can give is the cardiac pacemakers, where you see that many people would have taken a cardiac pacemaker um, when they have a problem with heart. The pacemaker was inserted into them by having an operation and would be given the pulse periodically to pump the heart. Whereas when that lifetime of the battery has gone, even though the person is healthy, still for replacing the battery, he need to undergo a surgery. Again, it is economically not possible that he has to pay for the surgery, then the battery has to be replaced, he need to be hospitalized and has to undergo some physical problems like pain and other sort of things to be since the person underwent an operation. And also sometime it may also end up in unavoidable circumstances like fatal error or something. So these kind of implantable energy harvesters can increase the life of the pacemaker, that he don't need to go for a surgery. Rather, our human body heat or the heartbeat itself provides the sufficient input mechanical energy which it requires to power that pacemaker continuously. So and then these wearable electronics, again when coming into the commercial market, they are having potential or enormous growth in several sectors, such as um, applications in business operations, security systems, medical application, sports, fitness. All these days we are using like having the smartwatch in hand and tracking the fitness and sports applications and all kind of how many steps I'm walking, what is the heartbeat, pulse rate, and all. But although the thing is like they are bulkier, but we wanted to go for a miniaturized one. So as such, we spoke about triboelectric effect. So we see you might see from this balloon that you can understand what is this triboelectric. So as simple, I want to say as the everyday static electricity is the triboelectric that we would have checked during our childhood. That rubbing the comb to the hair and try to pull the paper or some plastic to see the triboelectric. So this triboelectric also have positive and negative materials. So these positive materials are like this for glass, mica, nylon, and all. And these negative materials like polythene, polyethylene, PDMS, all these are the negative material. Uh, so when designing a triboelectric nanogenerator, we need to select the higher the positive and higher the negative, so that we can get most of the electrical output generated. And the other thing is also the surface roughness. So the surface engineering also plays a major major role in generating the electrical output. The higher the micro roughnesses we have in the surface, we can able to get or multiply the output generated, because when there is a flat surface, the contact point would be single, whereas there are micro roughnesses over the surface, the contact point multiplies. Thereby, the generated electrical output also multiplies. So let's see piezoelectric nanogenerator. This is also, we are well versed with piezoelectric effect, which is the ability of material which can generate charge when you apply some kind of a mechanical stress over it. So when we are making it as a device, so it's going to be called as piezoelectric nanogenerator, particularly if you have used nanomaterial into it. If the bulk material you have used, it's going to be a piezoelectric generator. So several examples are zinc oxide, barium titanate, sodium potassium niobate, and lead zirconate titanate. All these are the piezoelectric materials. And there is another effect called hybrid effect, where in that hybrid effect, we are going to combine both tribo and piezo into it, so that the electrical output increases. So some examples and the piezoelectric devices that we would be seeing here is the self-powered muscular monitoring system using piezoelectric composite strip via groove technique. So where we have made a mechanical grooves to make a very flexible uh, a piezoelectric device, where this work has been published in the cover page of the journal Nanoscale. So as you see in the schematic, that we have made a PET sheet and we have made a groove into it. So where a titanium wire is hung, so it doesn't touch any of the surfaces where it was in hang. And then we used here the opposite wire that if we put on our skin directly can undergo damage. So that's why we put it on the flexible bandage. So on the bandage we have kept, and the titanium wire in the middle is going to act as a one electrode, and the top electrode we are coating with Ag, with silver. And then again we have copper. To check its reproducibility, we went for 3 devices, where all 3 devices were producing very good electrical output. And then we have taken a glove to test it for the real-time application, made 3 devices to put on 3 fingers of the glove. And then when we are doing any kind of flexion extension using this hand grip and moving with the bare hand, the device started to response for it. And then the 3 devices were connected serially and parallelly, and it started to obey the electrical property. When we connect in the series, the voltage increases. When we put in the parallel, the current start to increase. And further extending that work, so we put on the various places of our human body, and we check whether the device started to respond for these mechanical motion. Even when we are moving the jaw, you can see the E figure, the breath pattern also could be analyzed using that one. So proving that this is one of the promising candidate to have the biomechanical energy scavenged to have been used for real-time application. Then there was a planar device that we have fabricated. So these planar device has been used for a sleep monitoring system. So as you know that this fits and epilepsy is one of the uh, thing which happens, jerking movements while the people were in sleep. So these days kids were also um, suffering with this kind of problem. So if a person is continuously monitoring these kind of symptoms, that we can able to know um, that it can be tracked continuously. So what is happening, whether it is getting affected or all the kind of thing. um, so that you can see in that video that how it is going on, that these kind of a small movement um, can be easily identified, that in the oscilloscope that you are seeing that the signal keeps on showing that what exactly is going on, and all these things. So it could be one of the very good tracking system to mm, to track it. So the next one is the fabrication of porous piezoelectric nanogenerator using this PDMS and BT1 nanoparticle. So this porous device that you can see, um, we have created micropores, so which is made of barium titanate nanoparticle. So where the XRD results are showing that um, the formation of barium titanate nanoparticles, and the Raman spectroscopy and the PE loop confirms the ferroelectric behavior of the material. And then where you see the composite film at the bottom, you can see we have created micropores. This was used by a simple technique while preparing the material. We used water droplets into it. So these water droplets, once we were heating it, so they try to uh, expel from that film, creating leaving the pores. And then that is the device where you can see in the F figure and can be used for energy harvesting. So this is the typical working mechanism, where in the C figure you can see that the dense film and the porous film. The dense film is kind of like you can see that it's a plain film, whereas the porous film, um, you can see that um, there is micropores, and the pores started to trap the charges which generated. These trapped charges are going to contribute in enhancing the output. Thereby, you see that charge enhances in case of the porous film. So further, if you see that we have analyzed the triboelectric, piezoelectric, and hybrid combinations, where the electrical response is higher in terms of the hybrid mode. And in the terms of the um, other, we see individual peng and teng components. It's not the case; they are reduced. So that's what we go for hybridization to enhance the generated electrical response. So further to it, if you see that the next slide, we try to go for taking the stability test, where the stability of the device has been identified. So which can go for 1600 seconds without affecting any of the um, without any interruption. And then we have calculated the power density, and the commercial capacitors has also been charged using this one. And you can see that in 100 seconds, a 2.2 microfarad capacitor was charged to 2 volt, leading to the real-time application. And then you see that the biomechanical energy harvesting of powering up electronic component, where we powered few LEDs and wristwatches into it. And then we went for an application of impact sensor, where we taken a bicycle helmet and put device on all four sides. And the initial laboratory testing, we used a tennis ball, and then the tennis ball would have some weight. So from different distances, we started to throw the tennis ball on the helmet where the devices are mounted. So where you see that in case of front and right, G figure 1 to 3, 1 and 3, you can see the first peak comes in the positive side, whereas in the G figure 2 and 4, the first figure comes in the negative side. So showing that we can able to differentiate which side it is hitting, because front and right are connected with the positive peak, and then back and left are connected with the negative peak, to analyze which side the impact has been hit. This can be used for advanced sports trekking and some athletic activity kind of application. So this work has also been published in Advanced Materials, Applied Material today in elsewhere. And then the other work was the porous multi-layered the device. So here we used barium calcium zirconate titanate as the parent piezoelectric material, and then we have doped holmium oxide into it, to enhance the piezoelectric property, and the multi-layer will increase the electrical output, which is doubled. So where you see that we optimized in figure A and B, the 10 weight percent of particle to the polymer was the optimized weight ratio. So further to that, we again check the tribo piezo and hybrid effect, where the hybrid device is producing 250 volt of electrical output. Where you see in the parallel connection, we try to increase the current for the application. So when we connect four devices into parallel, the electrical output was around 6 microampere. And where you see a 10 microfarad capacitor itself charged to 3 volt in 100 seconds. The previous one, you see that we have charged a 2.2 microfarad to 2 volt. Here, due to the multi-layer, a higher rated capacitor was charged to 3 volt in 100 seconds of time. So that is the power of going for a multi-layer. And here also we have powered up few electronic components to show the real-time application. And then it was used as a counter device, which can count the number of exercise repetition when it was attached to the human body. And also we have used it as a self-powered remote control to indicate the IR LED. and then a fire alarm detector, where you see that the device was connected to the fire alarm. When we turn on the fire, so it started to beep. So we entirely replaced the battery and the commercial electric power with this device. And the next one is wearable triboelectric nanogenerator from waste material. So this one we did from collecting the laboratory waste material, where you see the first one as the triboelectric device, where the two layers, the one layer is made of the tissue paper we throw in the laboratory, we recycled it, and we have coated it with carbon nanotube. And the second layer is waste coffee cup lid we have taken, and that material we analyzed in Raman spectroscopy, and it was PTFE. So we use it as a opposite layer, where the PDMS, which is coated into the individual fiber of the tissue paper, can be seen in this FESCM images. And they were giving very good electrical response of around 2.5 microampere of current that we were receiving. That you can see the device is very stable even at different forces that we have given. And with respect to the increase in force, we can see that the electrical response increases, and the stability of the device goes very high using this one. Um, and in the other case that we can see here, um, that we go for a real-time application of Morse code transmission. So Morse code is like an emergency signal, which we used to do, that we made it like a wristband, we put it on the hand and produce different Morse code, that you can see that I transmitted danger and TENG in figure D, you can see in the bottom. And this has been transferred as SMS or email notification to our mobile phone itself, which can be seen in figure E. And other than that, we went for a triboelectric based keypad. So the normal keypad, you would be either connecting it with power supply through USB, or you would be connecting it with the battery, if it is the case of wireless keyboard. So here each triboelectric nanogenerator acts as a key. And when I start to tap this keypad, so you could have seen here that the respective keys will be started to activate. So now you see in the video, which is playing in the side, that the L letter was made, and then O is made, and then yeah, and the different numbers. Now it is V. So like that it can be. So this work has been published in 2022 in ACS Applied Materials and Interfaces. Uh, and the other one was waterproof device, which is prone to humidity, where you can see this device also producing very good electrical output, that it blinks around 100 LEDs. And you can see in the below video, I put on the water tub and I am actuating it. So you can see the device produce stable response. If it is not responding to, if it is respond to humidity, you would be not getting the electrical output peak. It will just come as a single line. And other than that, we go for a hybrid nanogenerator for harvesting wind energy. We made a small wind tunnel structure and put the same triboelectric device. And we kept an electromagnetic device also. So the bottom figure is shown like in whichever direction the wind comes, the corresponding LED will start to glow. So showing the wind direction monitoring. So which we gave some wheels on the bottom for rotation and the wind vane. So it will automatically rotate to the direction of the wind it comes from. So here we created a surface roughness to multiply the output of the Kapton film which we used using inductive coupled plasma etching technique, where you can see A, B, and C figure that how we have created a micro roughness here. So each of these is 1 centimeter, 1 micrometer scale bar, and a 500 nanometer scale bar also have been attached here. That you can see a nano sized micro roughness has been created throughout. So where you can see from the plane, condition 1 we use oxygen and argon. Condition 2 we use oxygen, argon, and CF4. And condition 3 we use again oxygen and argon. The condition 1 is only oxygen. So where we see that oxygen and argon could be able to create very good micro surface, leading to generation of very good electrical output. So here also we glow 100 green LEDs in the hybrid combination, but we can able to get a broadband operating frequency. That is where we can able to trip of moving to Malaysia, but suddenly we had a
Yes, I understood. No
immediate
problem.
agreement for an MOU, so we quickly moved here. So I'm giving it from
No
Malaysia.
problem. No. So I think there is no question in the chat box. Thank you, Vivek.
Yeah, thank you, Dr. Siktipandi, for your
Okay,
invitation.
thank you. Okay,
Yeah,
thank you.
thank you. Yeah.